So in this video, I would like to take a little bit of time to talk about several issues involving the trigonometric ratios sine, cosine, and tangent. So, you learn SOHCAHTOA, you figure out how to use it. You probably have decent success in doing those things. We did that in another video. But what do those things, what do sine, cosine, and tangent actually do? What shortcuts do they allow us to take? Why do they work? So what I'm going to try to walk you through in order to explain that is this screen. So what I have on the left side of the screen is I have the smaller right triangle. It clearly has the right angle here. Angle C is a 90-degree angle. And then the other angles of that right triangle are angle A and angle B. So I haven't necessarily specified those with measurements just yet, but we're going to just refer to those angles as A and B. And the sides of this triangle measure 3 units vertically from A to C, 4 units horizontally from C to B, and then side AB would measure 5 units diagonally. You can hopefully remember the idea of a Pythagorean triple from when you were introduced to the Pythagorean theorem way back when. If I take 3 squared plus 4 squared, that's 9 plus 16. That's got to give me the hypotenuse squared, got to give me 5 squared. And 9 plus 16 definitely does give me 25. So there aren't really a large list of nice values that form Pythagorean triples. A lot of right triangles end up with sides that measure with some irrational length. That's not the case for a Pythagorean triple. With a Pythagorean triple, you're going to end up with nice rational values for the measure of all 3 sides, and that's exactly what we have for this triangle here. Now let's say that I wanted to blow this triangle up, make it bigger. Let's say I wanted to make this side have a length of 9 units as opposed to 3 units. Well, how do I get from 3 to 9? I triple it. So I triple the length of the side that measures 3 units to get the length of the new side. I triple the length of the hypotenuse to get the length of the new hypotenuse, and then I triple the length of side CB to get the new length of side CB on the enlarged triangle. Now, if I enlarge the triangle this way by just keeping the sides proportional to one another, what happens with the angles is they all remain the same. So you might remember the triangle similarity postulate, angle, angle, angle. So if all 3 angles of a actually just can be angle, angle, because if you have 2 angles the same, it's assumed the third angle's got to be the same too. But if you have the 3 angles of a triangle measuring the same length, those triangles are similar to each other. And if you remember anything about similar triangles, the lengths of the sides are proportional to one another. So how does this relate to sine, cosine, and tangent? So I'm going to take these triangles to a new screen, and I've done a little bit of work with sine, cosine, and tangent. Angle A on the small triangle measures the same as angle A on the big triangle. These triangles are similar to each other, and similar triangles are always going to have the angles measuring the same. So the sides don't necessarily measure the same on similar triangles, but the angles do. And we have proportionality between the corresponding sides on the smaller triangle with the bigger triangle. So check out what happens if we do sine of angle A. Regardless of which triangle we look at, these angles are the same on the 2 triangles that sit in front of us right now. So using SOHCAHTOA, sine is opposite divided by hypotenuse. Well, if I do opposite angle A on the small triangle, I get a 4, and divide by hypotenuse on the small triangle, I'm going to divide by 5. So sine of angle A on the small triangle is going to be 4 divided by 5. Sine of angle A on the big triangle, if I take the same approach, angle A is still in the upper left. Angle A measures the same on the 2 triangles since they're similar to each other. Sine of angle A is going to be opposite divided by hypotenuse. So that would be 12 divided by 15. Think about reducing this fraction. Top and bottom of this fraction can both be divided by 3. If I divide top and bottom both by 3, I reduce it to 4/5. So no matter which triangle we look at, the smaller triangle, the larger triangle, I'm going to have sine of that angle, that ratio of opposite divided by hypotenuse. It's going to be the same no matter which triangle I build it from. Let's say we even had a third triangle that was similar to these two. Let's say we wanted to have the size of a new triangle be 100 times the size of this triangle. So if I multiplied this into a 300, multiplied this by 100 into a 400, and then multiplied this by 100 into a 500, I could also do sine of angle A on that even larger triangle, and I would still get the same numerical value. The numerical value here is zero point 0.8 if you write that as a decimal. So the sine, cosine, and tangent ratios, they allow us to kind of take some shortcuts through triangle similarity work because similar triangles, triangles that have the same angles that are also right triangles, similar triangles are going to have proportionality between their sides. Sine, cosine, and tangent take out the intermediate steps of building those proportions and solving for unknown sides. Eventually, sine, cosine, and tangent will allow us to solve for some unknown angles. You see I have a couple other calculations done here. Cosine of angle A, same thing's going to happen. Cosine from SOHCAHTOA, CAH. So if I look at the small triangle and relative to angle A, I take adjacent divided by hypotenuse. That'll be 3 over 5 or zero point 0.6. If I do that for the big triangle, angle A is still up here. Adjacent divided by hypotenuse is going to be 9 divided by 15. This fraction reduces to that fraction. Both of these fractions have a decimal value of 0.6. So sine, cosine, and tangent ratios work because triangles that are right triangles, which sine, cosine, and tangent apply to, that have the same angle measures, are going to be similar to each other. Sine, cosine, and tangent take all that work with proportions out of the mix. They've already done that work for us, and they also allow us to relate angles with sides. So hopefully that's kind of allowed you to understand what sine, cosine, and tangent do, why they work. They work because of triangle similarity. And that's not necessarily something I addressed within that first video where we took some time to introduce sine, cosine, and tangent.